All right, hello everyone and welcome to this video. So this is after a lot of wait and I'm sorry I haven't been uploading for so long. I've actually got stuck up with some things of my own. But anyway, this is a test that was on the unit 3, which is of waves. So general waves, EM spec, light, lenses, sound, all of that. So it's like a pretty good test for you to actually see how much of your syllabus you know. It's from the more recent past paper questions. And this is overall a great way to assess your units. So for example, this is unit 3 on waves. I also have had tests for my students for units 1, 2, and 4, which are also pretty important. So this way you like basically tuck away a really big portion of your syllabus and you assess that in that unit, where are you getting stuck with which chapter. So that's the idea. So this was a 60 mark paper and it's kind of not really according to the Cambridge structure because it's supposed to be a small test. So this is 1 hour 15 minutes for a 60 mark paper. All right, so let's get started. Question number 1. Which statement is correct? Both longitudinal waves and transverse waves can travel at the speed of light. So we know that the transverse waves that do travel at the speed of light are the electromagnetic waves. Do we know of any such longitudinal wave? No. So this is not the answer. Both longitudinal waves and transverse waves of similar wavelengths must have similar frequencies. This seems like a pretty normal statement because if I think about the wave speed equation, if they have like some wavelength, then they would also have some frequency corresponding to some speed, right? Both longitudinal waves and transverse waves can travel in a vacuum. This is not true. So longitudinal waves do not travel in a vacuum. Any of the examples we know, sound or anything of that sort. So it doesn't travel in a vacuum. Both longitudinal waves and transverse waves can travel in water. Now, is this statement true or false? So when we think about this one, okay, so for this one, option D, this says both longitudinal waves and transverse waves can travel in water. This also makes sense that, for example, sound can travel in water, and for example, like water waves themselves, which are transverse waves, can travel in water. So this is correct. Now, why is D wrong? Why is B wrong? My bad. So B is wrong because of this word which says must. It's not necessary that something which has the same wavelength, so if a transverse wave and a longitudinal wave have the same wavelength, they don't necessarily have to have the same frequency because that implies that the speed is the same. So this is not true. For example, if I'm talking about sound and if I'm talking about light, so let's say they have a wavelength 0.5 meters, they're not necessarily going to have the same speed. So that's why B is wrong. Question number 2. A water wave on a pond passes into a region where the wave travels more slowly. It then returns to a region where it travels at the original speed. Assume that the frequency of the wave stays constant. And the question says which side view of the wave is correct. And something like this is asked a lot in graphs as well. So the idea is this, that if it slows down in entering this new region and the frequency is constant. So if I think about the wave speed equation, so frequency is constant. If the wave is slowing down, this means that the wavelength must have decreased. And if you're looking at a side view of the wave, or if you're looking at a picture of a wave, that's basically going to tell you the wavelength if you, for example, look at the peak to peak distance. So here there is some peak to peak distance, then it decreases. I can also look at the wavelength in terms of the start and the end of the wave. So that's this. This is smaller as compared to that, and then it increases again. This is correct. All right. A vibrator produces 12 wavelengths on the surface of water in 10 seconds. Spacing between the first and the third crest is 60 cm. What is the speed of the wave? Now regarding wave production, wavelengths or crests or wavefronts or waves, all of these mean the same thing. So if 12 waves are produced in 10 seconds, I can figure out the time period or the frequency depending on how I talk about it. For example, if I talk about the frequency, so if you have 12 wavelengths in 10 seconds, so frequency is basically how many waves you have in 1 second, that is 1.2 here. And then if I talk about the wavelength, basically if this is the spacing between the first and the third crest, so 1, 2, 3. So if this is the spacing, they're saying that this is 60 cm. And if I look at the graph here, this is two wavelengths because this is 1, this is 2. So the actual wavelength is half of this, that's 60 over 2, that's 30 cm. It's the same thing, for example, if it said between the first and the fifth crest. So look at your fingers. You have, imagine that each of your fingers is a crest. So you have 5 crests, but the spaces in between are the wavelengths. So that would really be equal to 4 wavelengths. Now once you have this, you just use the wave speed formula, V equals to F lambda, you multiply the 2 and you get 36. Which statement is correct? Total internal reflection occurs only when light travels from air into glass. First of all, this is a pretty narrow statement. Generally, it occurs when light goes from a more dense to a less dense medium, and here it's the other way around, so this is wrong. The larger the refractive index of the glass, the larger the critical angle. This is also wrong because we know the formula is this, n equals 1 over sine c. And basically how the sine function works is if the angle gets bigger, as long as we're talking about acute angles, the sine of that also gets bigger. So that would mean that if my refractive index is larger, the critical angle would be smaller. So this is not it either. When total internal reflection occurs, the angle of incidence is equal to the angle of reflection. This is absolutely true because in any reflection, be it just normal simple reflection or total internal reflection, the angle of incidence and the angle of reflection are equal. When TIR occurs, the angle of incidence is less than the critical angle. Not true. So on TIR, you have two conditions, that the angle of incidence must be more than the critical angle, and additionally, you must be going from a more dense to a less dense medium. Next question. A mirror is placed in the path of a ray of light. This is the incident ray, this is the normal ray. This is the normal, this is the reflected ray. Through which angle does the direction of the ray of light change? Now what this means is, and that's why this line is drawn on the paper, on the question. So you are told the path of light without the mirror. So if there was no reflection, this is how it would have gone. But it's going like this. So all I need to use for this are some angle properties and just a little bit of math. So if this is 40 degrees, I know by reflection this is also going to be 40 degrees. Because this is the normal, which makes this angle 90, I know this would be 50. And similarly, this would be 50 as well. And again, because these are straight lines, so if this is 50, then this would also be 50. So this is the path of light without the mirror. It changes through this direction. So this angle is 50 plus 50. That's 100 degrees. A ray of light passes into a block of transparent material as shown. What is the refractive index of the transparent material? So the first thing you should note in this is that neither of the angles are with the normal. So you first need to calculate that. If that is 35, this is 55 because of 90 minus 35. And if that's 60, similarly, this is 30. So when we talk about the refractive index, that's the sine of angle in air, or you can also say the sine of the bigger angle divided by the sine of the smaller angle. So sine 55 divided by sine 30. This turns out to be 1.638, so 1.64. Next. Which statement about human vision is correct? In a normal eye, the image on the retina is magnified and upright. Now, is this true or not? The image on the retina may be magnified, but it's definitely not upright. It's an inverted image, and then the brain inverts the image again. In a long-sighted eye, distant objects from images form in front of the retina. So how I want you to remember long-sightedness, this is also in the lenses video playlist, that in long-sightedness, the image forms a long distance after the lens of the eye, so it's found behind the retina, it's not in front. Short-sighted eyes produce only virtual images. Now, is this true? So this is also not true, because any sort of eye does not produce virtual images. It produces real inverted images on the retina. And even if this is not on the retina, this is still a virtual image. And this is corrected by the use of a diverging lens, because if this is your eye, so the rays converge on in a short-sighted eye here. So you need to make it converge here. So you would use a diverging lens to further diverge the rays so that they meet here. Alright, so it's this which is your answer. A boy stands behind a girl in front of a large vertical plane mirror. Their equal distances from the mirror is shown. The boy sees an image of the girl. Where is the girl's image? So I know that the boy, if he is seeing the girl's image, so that's like this. So rays from, so this ray from the girl to the boy is what he must be seeing. But the idea behind ray diagrams is also this, that the image is formed behind the mirror. So if I take this back, this is how the boy must be seeing the girl. Because if this is where the girl is, the image is formed in equal distance but behind the mirror. A ray of light R is incident on a water to air surface with an angle of incidence theta. The angle theta is less than the critical angle C. So the angle must be more than the critical angle for total internal reflection. So I know for a fact it is not going to be totally internally reflected, right? So I know that some of it is going to be refracted and some of this is going to be reflected, but normally the sum of it being reflected part, it's not really part of your syllabus. So let's see how it's going to be. So this is going from more dense to less dense. So I know this is going to bend away from the normal. So this is what I would expect. So it travels back into the water with an angle of reflection equal to C. So that's not really true. Most of it is refracted. No, again, this is just a violation of reflection. It travels into air with an angle of refraction greater than theta. So this is your angle of refraction, which is obviously going to be more than theta. So this is your correct answer. Question 10. An ultrasound scanner produces an image of an unborn baby. What does the scanner use to form an image of the baby? So this is something I've talked about numerous times, that for an ultrasound, the receiver and the transmitter are the same probe. So we basically use the reflected part to form images. So that's C. 11. Now this is a sort of a tricky question, because anybody and everybody who knows the echoing formula, they just can't use the formula to do this question. So it needs a little bit of thinking. So a man stands between two tall buildings P and Q. He is 50 meters from P, 200 meters from Q. So this is building P, this is building Q. He sounds a horn. He hears the first echo from building P, obviously because this distance is less. And 1 second later, he hears the first echo from building Q. So now what we know from this is that there is a 1 second difference between hearing these echoes, right? So if I find this out, I can say that some time is taken, let's say T1, for this echo to come. So I can say that this time, because speed is distance over time, so time would be distance over speed. So T1, I can say, is the distance, which is 100, 50 on the way to the wall and 50 back. 100 divided by the speed of sound, which is exactly what we are asked to calculate, which is V. Similarly, this one, let's call this time T2, and I can use the same idea here as well. So 200 on the way to Q and 200 on the way back. So the total distance is 400 divided by v. Now I obviously know that this time is going to be less, this time is going to be more. So I can subtract these times. So t2 minus t1, that should equal this 1 second. So that's what I'm going to do. T2 minus T1 equals 1. In a way, it's also kind of similar to those questions that you have in math where you have to set up the equation. That's why this one was more tricky. So 400 over V minus 100 over V equals 1. No need to take LCM. The denominators are the same. So 300 over V equals 1 multiplying by V. So V turns out to be 300. The answer is option B. Sound waves are displayed as a trace on the screen of an oscilloscope. Which trace shows the sound that becomes quieter with a higher pitch? Quieter means amplitude goes down. Higher pitch means frequency goes up. So this is shown on an oscilloscope. All right. So an oscilloscope, now this is different from the question that we did earlier because that was just a side view of the wave. This is on an oscilloscope. So on an oscilloscope, I know that y-axis is voltage and x-axis is basically time. So higher pitch would mean frequency goes up, so the wave gets narrower. So that's happening in this. Yeah, it's only happening in this. And as you can see, the frequency is going up, amplitude is decreasing. Okay, frequency is going up. All right, frequency is going up here. No, so frequency is also going up here, right? Yeah, my bad. Because you also, this versus this, so this is definitely smaller. But then amplitude going down. So amplitude going down is not happening here. That's here. This is your correct answer. So the amplitude also decreases. Ultrasound is a type of sound wave that is not audible to a healthy human ear. We know this is the frequencies which are more than 20,000 hertz. Which range of frequencies contain only ultrasound? So 30 hertz to 3 kilohertz, definitely not. Again, it says only ultrasound. So anything ahead of 20,000 and the other range must also be ahead of that. So 3 kilohertz to 3 megahertz, not this. This is true because both of these are greater than 20,000 hertz. That was the MCQ section. Let's get started with the structured questions part. 1A 8.1 shows a ripple tank in the crests of the water wave that is produced in it. Frequency of water wave is given, so I can figure out the time. Amplitude is 3 millimeters. Calculate the number of crests produced in 1.5 seconds. So 2 hertz means that 2 waves are produced in 1 second. So in 1.5 seconds, you would have 3 waves being produced. Right? Simple unitary method. Height of the water wave is measured from the level of the undisturbed surface at the water. Height of the wave at one point is 0 at time t equals to 0. So we know the starting position is going to be this. And then it says draw a graph to show how the height of the wave at this point varies with time. All right, so I know the amplitude as well, so it's 3 mm. So I know that in 2 hertz, which means a time period of half second, by this formula, t equals 1 over f. So 1 over 2 is half. So in this much time, I must have one wave, then another wave, and then my third wave. So I know that how it's going to be now is basically a shape like this. Wait a minute. Like this. So I know the amplitude is 3 mm. So I know 3 mm is going to be here, smack in the middle of 2 and 4. So 2.5, 3, 3.5. Okay, so each small box is 4. So the division between these two is 4 boxes, not 5 in this case. So at this time here, so at 0.25, I know it's going to be 0 again. because the graph is going to come back down, and in the middle here this is 3, and then here in the middle it would be -3 again. So is that fine? This, yeah. So I know that how the graph shape would look like is this. So like this, and then like this. And this is basically the graph shape that's going to keep repeating. So let me just copy paste this now. So then this, and then my third shape, which is this. All right, so that's how the wave is supposed to look like. Frequency of the wave is increased. Describe how the apparatus shown in 8.1 is adjusted so that the frequency is increased. So it's based on the apparatus. So for the apparatus, we can see that you are basically using a rubber band to stretch this, to basically give this wooden bar oscillations. So if you stretch the rubber band more, so this is then going to hit the water more often. So this is going to basically create more waves, and that's the idea of more frequency. So you can just say stretch the rubber band more, and release. Okay, so on second thought, if you stretch the rubber band more, it's not really going to change the frequency, it's just going to change the amplitude. So to increase the frequency, you can just say this, that you can move your bar up and down more. But again, how would you do that using rubber bands? Is, for example, you can say that you use stronger rubber band so that it's pulled back more and it stretches more and it hits the water more often, right? And you can also say that, for example, you use a lighter bar because that would also make it hit the water more often, right? So I'm going with the second one. So let's say you use a bar of lesser mass. State what happens to the speed and the wavelength of the wave as frequency increases. Medium is not changing here, so the speed is constant. And because frequency is increasing, for the speed to be constant, wavelength must be decreasing. The apparatus shown in 8.1 can be used to show refraction. State the additional apparatus needed to demonstrate refraction. So we know you need a glass block to create those regions of deep and shallow water. Draw on 8.3 to show the refraction of the water wave. Label a boundary where refraction happens. All right, so no need to basically create more work for yourself. Let's say this is the boundary, so I've taken the easier case, no shame in that, where refraction is going to happen. So this is my wave from here that's going to basically be incident on the boundary normally. The other possibility is you took that one where it's not basically incident normally, where it would basically make an angle, but the drawing is a bit more difficult. That's why I'm just going with this. So what you and your diagram should definitely show is that if this is going from between these boundaries, so this is the glass block region, so this is where this is shallow water, right? Remember the acronym SH shallow, SH shorter. So this is that part. So let me also label this. This is deep waters and this is shallow. All right. So this is good enough. Okay. 8.4 shows a connection to the internet made from a remote station A using a satellite above the Earth's surface. Data is sent between stations A and B using microwaves which travel to and from the satellite. B is connected directly to the internet using optical fiber. Speed of microwaves is this much. Stations A and B are each 560 kilometers from the satellite. Calculate time taken for data to travel from A to B using microwaves. So this distance is 560, this distance is 560. I know the total distance is 1020. I know the speed even if it was not given, so I can find out the time. So time is distance over velocity, as we just used in the sound MCQ as well. So total distance is 1020, so 560 times 2, but this is kilometers, so multiplied by 10 to the 3 divided by 3.0 into 10 to the 8. So 1020 to 10 to the 3 over 3.0 into 10 to the 8. This is 3.4 into 10 to the negative 3 seconds. The same data can be sent from A to B in a shorter time along the surface of the Earth using infrared waves to carry the information in optical fibers. State one property that infrared waves and microwaves have in common. So I can say anything that is basically common to electromagnetic waves. So I can say both can travel in a vacuum. Suggest one other advantage of using optical fibers to connect stations A and B directly. So they've already said that it's a shorter time, right? So you can say something like this, that it's more secure data transfer, or you can say it's larger bandwidth, or you can also say that you don't need a satellite with that, right? So yeah, any of those is fine. Question number 2, ripple tanks are often used to illustrate wave motion. Describe what is meant by wave motion in a ripple tank. So wave motion means the transfer of energy without net transfer of the medium. If you go back and watch my waves video, you'll see that this is the first thing I discuss in that one. And additionally, you can also say by vibration of particles. So by vibration or oscillation of particles. When describing wave motion, state what is meant by frequency. So frequency is number of waves in 1 second. And additionally, just to further clarify this, you can also say that are being produced, or you can also say passing a point. Wavelength, so usually the definition is it's the distance between two consecutive peaks or two consecutive troughs, but in the more recent mark schemes we are seeing this definition, which is why I'm going to write this here, that this is the minimum distance between 2 points that have the same displacement and velocity. And obviously the peaks or the troughs, they fall under this category, but this is slightly better to write. A water wave in a ripple tank strikes a barrier. 4.1 shows some wavefronts of the incident wave. Wave hits the barrier and is reflected. 3 of the wavefronts have already hit the barrier. Reflected parts are not shown. Draw the reflected parts of these 3 wavefronts. So first of all, the normal, then the reflected parts, and we've talked about this, that when you make reflected wavefronts, make sure that according to symmetry, because the angle of incidence and the angle of reflection are also equal here, they must intersect at the normal. So for example, if I need to make of these 3 wavefronts which have already struck here, so for example I can make this one, right? So as you can see by symmetry, so this is basically the reflected part of this one. So this one is this one right here, right? So this and this angle also visually seems the same. Again, basically the idea that I've used here is this. This is not something that the examiner gives marks on. I am skilled enough to do it without this, but if you feel a bit skeptical, you can do this. That if this is the direction of the incident wave, the direction of the reflected wave is at the same angle with the normal. This that I've drawn here is the normal. And this is the direction of the reflected wave that I have here. Then the other parts, so for example, this one is yet to strike, so only some of this is reflected here. So you can make it like this as well. So like this. And then the third part would basically look like this. Okay, so let me make this here. And then this one would be like this. All right. But because this one would also be moving like this, so that's why I prefer to draw it in this way. Like this. So for example, just get rid of this for a second. So this one, and for example, this one. Okay. Just a minute. Okay, so because you have to draw the reflected part, let me also make another possible drawing. So let's say this is the wave front corresponding to this one. So for this one, obviously it would be something like this. Maybe it's gone a bit far ahead, like this. For the other ones, I should take care that the wavelength does not appear to change because it does not change on reflection. So for example, this is the reflected part of this one, this is the reflected part of this one, and this is the reflected part of this wave, right? Again, visually the wavelength must not change, and if this is going a bit ahead, you can just get rid of this. So that's how the drawing is supposed to look like. Question 3. Ultrasound of frequency 30 kHz has a wavelength of 0.011 meters in air. State what is meant by frequency. So this is the number of waves or cycles produced in 1 second. Or you can also say passing a point in 1 second. Calculate the speed of ultrasound in air, show your working. So V equals to F lambda, pretty straightforward. F is 30 kilohertz, wavelength is 0.011, so you just multiply these. So this is 330 meters per second. State one use of ultrasound. So you can do a lot of these. For example, jewelry, cleaning, sonar methods, or prenatal scanning. Sound waves are longitudinal waves, water waves are transverse waves. Describe by referring to the movement of particles in the wave the difference between a longitudinal and a transverse wave. You may include a label diagram, but you don't have to if your explanation is crystal clear, which is what mine is going to be. So for transverse waves, have the direction of wave motion. Instead of wave motion, if you want to call it the direction of energy transfer, that's also fine. Of wave motion perpendicular to the direction of energy to the direction of, okay, let's write it like this. Instead of wave motion, let me first write particle movement. That's what the examiner says. So particle movement perpendicular to the direction of wave motion in longitudinal waves direction of particle movement is parallel to the direction of wave motion. There's pretty much, this is all there is to it. So yeah, that gets you 3 marks. State one source of waves that generate both longitudinal and transverse waves. So a pretty easy one is seismic waves. Seismic P are longitudinal waves, seismic S are transverse waves. 4.1 shows radio waves of long and short wavelength passing over the same hill. Explain why the radio waves in diagram A reach the house but the radio waves in diagram B do not reach the house. Just by the look of this diagram, you can see this is diffraction. You can see that these ones have a relatively larger wavelength as compared to this, and you must know the link between diffraction and wavelength. So you would say this, that the waves in A have a larger wavelength so they diffract more to reach the house. Easy. Or you can also say that in B they have a smaller wavelength, so they do not diffract as much and they do not reach the house. 4. A student directs a beam of white light from a filament lamp towards a glass prism in a dark room. 4.1 shows the beam of white light incident on the left hand side of the glass prism. A screen is placed to the right of the glass prism. Red light is observed at R and violet is observed at P. Draw on 4.1 to show the paths of the red light and the violet light between the left hand side of the prism and the screen at point R and point V. So for R, we know it's going to diffract less at each boundary. Sorry, not diffract, refract less at each boundary. It's also going to diffract by not a lot here to reach this. And for violet light, I know it's going to bend more at each boundary. So let's pick up that color. So this is violet light bends more at each boundary to be here. That's this. State what these observations show about the change in speed of red light and change in speed of violet light as each enters the glass. Alright. So the change in speeds of red and change in speed of violet. So we know that diffraction is because of changes in speed. So we would say that since red bends less, the change in speed of red is less as compared to violet. So red slows down less. Alright, so slows down is not written here. So let me just write this. How about I change this word to decrease? So the decrease in speed of red is less as compared to the decrease in speed of violet. So violet slows down more, that's why it also bends more. 5 other colors of light appear on the screen between the red light and point R and the violet light at point V. State the name of the 5 colors and list them in the correct order from red to violet. So we know this, VIBGYOR. So violet, indigo, blue, VIB, green, yellow, orange and red. State how the frequency and the wavelength of the colored light change in going from red to violet. So violet is the highest frequency, so frequency increases, but they all have the same speed in air, so wavelength decreases. On 4.1, point P is shown immediately next to point R. No light is observed, but a detector at point P registers radiation reaching the detector. State which region is detected at P. So if this is here, so just like in going from here to here, the wavelength was increasing. So this is even larger wavelength than your visible light. All right. So you know the mnemonic: raging Martians invaded Venus using X-ray guns. So higher wavelength than this means this one right here. So here we must have infrared. Similarly, if any radiation is given here, that would be UV. So P is infrared. Question 5. VR headset in 6.1 contains a display and a lens. Display is the object, lens acts as a magnifying glass and forms a virtual image of the display. Describe where the display must be positioned relative to the focal length for the lens to act as a magnifying glass. So magnifying glass we know is case number 6 of our lens cases. So we know it must be positioned between the optical center and so it says relative to the focal length. So between optical center, okay. So we must say, then let's talk about it like this. So within the focal length from the optical center. All right, so it must be between O and F. Explain how a virtual image is formed. So we would say that the rays in a virtual image appear to come from the image, but they actually come from the object. Part B, an arrow on the display is 3.4 centimeters from the lens. Virtual image is 22 centimeters from the lens. 6.3 shows the arrow, lens, virtual image on a grid with a scale of 1:2. That's also shown here. On 6.3, draw a ray diagram to show the formation of the virtual image I. So this is your object, this is your image, and this already looks like case 6 of the drawing. So let's use my ray rules. So I know that a ray through O is going to be undeviated, and if this ray is coming from the top, it would also coincide with the top of the image. So this is how this ray is going to look like. So like this. All right, and then I can use rule number 2. So this ray through here would be refracted like this, but again the problem is that I don't know the focal length, and in the next part I have to find the focal length. So what I do know is this, that this one, because it's from the top, it must again correspond to the top. So this is how this ray is going to look like. And if I take this forward, okay, now I can't do this, can I? Anyway, so if I take this forward here like this, so I can figure out the focal length here, right? So the ray rule says this, that a ray parallel to the principal axis passes through the focal length. So this is probably my focal length here. All right, so determine the focal length. So this is 2, this is 4, and this is going to be 6. So each small box is what, 0.4, 0.8, 1.2, 1.6, yeah. So this seems like 4.4 centimeters to me at least. So according to the marking scheme, this is supposed to be 4.0. So this is probably because of, yeah, you can see why this is. That's because of this. So if I just align this, I'll probably get the same answer. Yeah. Right, so this one would also then bend like this. So yeah, now this seems to pass through here as opposed to this. So that's 4.0. Okay, so that's basically this test. It was a very comprehensive one which dealt with all the chapters, all the units on waves. So you should also try this out without watching the video solution. For my students, I've already given them this test. So this video is meant for them to double check their solutions. So like this video, share it with a friend if you think they would benefit from this. Comment if you want any more videos or if you have any potential ideas, and I'll try to make them as soon as possible. Best of luck for your exams, and don't give up on the good work that you've been doing. Bye.